Up until this point, we have been learning about measuring statistical significance, in which we determine whether the differences observed in the sample were caused by mere random chance or actually have meaning. The statistic that we have focused on this week is the bivariate measures of association with nominal variables. Bivariate analysis is used to analyze the level of association between two variables, or rather, the relationship between them. When two variables are said to be associated, this means that the dependent variable changes in response to the change in various categories of the independent variable. With measures of association, we are testing for three things. We are testing to see whether there is a relationship between the two variables, how strong the relationship is, and what the direction or pattern of the relationship is. Therefore, the bivariate measure of association can not only tell us how strong the relationship between two variables is, but it can also allow us to make future predictions about how one variable might affect another variable. There are a few limitations in measuring association between variables, such as the fact that it can't prove that there is an actual causal relationship between two variables, even if statistics prove a strong association. Another limitation includes the possibility that two variables can be associated but still be independent of each other, meaning we fail to reject the null hypothesis. When you have a 2x2 table, meaning there are two options of the independent variable and two options of the dependent variable, you would determine the phi value. To do this, you would divide the value of the obtained chi-square by the total number of cases in the sample, and then take the square root. Although chi-square is used as a measure of statistical significance, it can also be used to determine the strength of association in this sense. The value that you get shows you the strength of association between your two variables. If your variables have more than two categories for each, you would use the Cramer's V equation. For this equation, you would take the lesser of the number of rows minus 1, or the number of columns minus 1, and then multiply this number by n, the number of cases altogether. You would divide the chi-square value by the number you have just calculated, and then find the square root. The value that you calculate signifies the strength of the association between your variables, similarly to the phi value. The interpretation of this number is the same with the interpretation of the phi value. If your phi value ranges from 0 to 0.1, your variables have a weak association. If it ranges from 0.11 to 0.3, it has a moderate association. And if the value is greater than 0.3, your variables have a strong association. But it is important to keep in mind that this value doesn't interpret the exact relationship between the two variables. Another way to measure the association between two variables is to use the proportional reduction in error, in which we quantitatively measure the proportional reduction in errors between the two predictions. The two predictions are that we ignore information about the independent variable, therefore it would make many errors in predicting the score on the dependent variable, and the second prediction takes account of the score of the case on the independent variable to help predict the score of the dependent variable. Another way to calculate the strength of association of two variables is by calculating lambda. Lambda measures the proportional reduction in error obtained when the researcher uses the value of the independent variable to predict the value of the dependent variable. If there is an association between our variables, we will make fewer errors. To calculate lambda, you would find your value of E1, which is n, the number of cases altogether, subtract the largest row total number. Next, you would find the value of E2 by subtracting the largest cell frequency from the column total for each column in your bivariate table, and then adding these subtotals together. You would then subtract your E2 value for E1 and divide that number by E1. The value you receive indicated the percentage of fewer errors you would make by taking your variable into account. The limitations of using lambda, though, include its asymmetry, in which the value of your statistic will vary depending on which variable is taken as dependent. Another limitation includes the fact that when one of the row totals is larger than the others, lambda can come out as 0 even when other measures of association are greater than 0. So, the first example given in the back of Chapter 11 for SPSS will be looking at whether health varies by income. After opening the 2009 GSS shortened data set, we will have to recode the variables because they each have too many categories. Click on Transform, then recode into different variables. Once the box opens up, click on the variable Income Household and click the arrow to bring it to the Output Variable box. In the far right column under Output Variable, change the variable's name to Income 4. Click the Change button. Click the Range button on the left and type 1 in the first box and 6 in the box below it. In the Value box, name it 1, and then click Add to add it into the Old and New Values box. We'll do this for the rest of the values as follows. 7 through 9, and name it as 2, 10 through 11, and name it as 3, and finally 12 through 13, and name it as 4. Once the values have all been added, click Continue, and then press OK. We will do the same thing for our variable State of Health, shown as SRH underscore Q110. Go to Transform, then recode into different variables. Click the variable SRH underscore Q110, and click the arrow to bring it into the Output Variable box. Name the variable Health. Click Change. Click the Range option and recode as follows. 1 through 3, named as 1, and 4 through 5, named as 2. Press Continue, and then press OK. Now, to compute the statistic, go to Analyze, Descriptive Statistics, and then Crosstabs. Click on our Health variable, and click the arrow to bring it into the row box. Click on the Income 4 variable, and click the arrow to bring it into the column box. Click the Cell button. Make sure Observed is checked off, as well as Column under Percentages. Click Continue. Next, click Statistics. When the window pops up, click on chi-square, click Continue, and then OK. Once our output is produced, we can observe our chart to see what the conditional distribution of each category is. By looking at the chart, we can see that there is a relationship between health and income, as we see that those with a higher income tend to have better health and vice versa. Looking at the ASIMP-SIG two-sided column under the chi-squares test chart, we see that the value of chi-square is 0. Because this is below 0.05, we can reject the null hypothesis. Therefore, we can conclude that there is a statistically significant relationship between income and health. For the next example, we will be looking at whether criminal victimization varies by area of residence. Go to Analyze, Descriptive Statistics, and then Crosstabs. When the box pops up, click on Life Vict and click the arrow to bring it into the rows box. Click on Luke Rest and click on the arrow to bring it into the columns box. Click the Cells button. Make sure the column option is clicked under Percentages. Click Continue. Next, click the Statistics button. Check off chi-square, phi and Kramer's v, and lambda. Click Continue, and then click OK. Once the output is produced, we can look at the chart of our variables to determine what the conditional distribution is of each. Looking at the chart, we can see that there does seem to be a relationship, with those living in urban areas more likely to experience crime. Looking under the chi-square test chart, at the chi-square row, we see that the value is 0, and therefore we know that there is an association. Under the directional measures chart, we can look at the 3 values reported for lambda. We must remember here that lambda is asymmetric and can change value depending on which variable we use as dependent. We look at the Life Vict variable for lambda, as it is our dependent variable. The value is 0, which normally indicates no relationship between the variables, but we must disregard lambda in this case because we saw that the conditional distributions in our chart did change. Lambda is misleading in this case because the row totals are unequal. The sample research question that we chose was, does gender affect whether a person experiences discrimination? So, go to Analyze, Descriptive Statistics, and Crosstabs. Click on Sex of Respondent, and click the arrow to bring it into the rows box. click Victim of Discrimination and place it into the columns box. Click the Statistics option and make sure to check off chi-square, phi, and Cramer's v, and lambda. Press Continue. Click the Cell option and click on Columns under Percentages. Click Continue and then OK. Once our statistics have been produced, we can see looking at our table that the conditional distributions are pretty evenly distributed, and so we can't gather much from just looking at our table. Looking at our chi-square chart, our asymptotic sig2 sided value is 0.324, and therefore we can conclude that there is no statistical significance, as this value is much higher than 0.05. We failed to reject the null hypothesis. Further looking at the phi and Cramer's value, to reiterate this, we have received values of 0.026. Because this number is extremely close to 0, we can conclude that there is a very, very weak association between gender and victim of discrimination.